In this lesson, we're going to review position, displacement, and velocity, and how we graph them and what those lines mean. So position, remember, is distance and direction from a reference point. The reference point is whatever it is we're using to describe the rest of our motion. A lot of times we use the motion detectors for our reference point. Distance is measured in meters. Direction we can say away from or towards. Remember, displacement is direction and distance between starting and ending. So displacement, which we give the symbol delta x, is distance and direction from start to end. Distance and direction from start to end. So this is review information. Now, let's take a look at one of those graphs. So we have a position versus time graph, which shows us an object's position at every instant in time. We're going to go 1, 2, 3, 4, 5, 6. 6, 5, 4, 3, 2, 1. And we'll make sure we give our units seconds. Over here we have position, often given the symbol x, measured in meters. And we'll go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now I'm going to draw a couple different motions on here. I'm going to have one line start here and go up to here, and then stay constant there for a few seconds, and then come back down. Alright, so if I have this motion, what does it show? Well, it shows that an object started at 0 seconds. Its initial position was 1 meter in front of the reference point, and after 3 seconds it had moved to 4 meters. So if I want to know how far it went, delta x, its displacement, that's always final position minus initial position. In this case, that's equal to 4 minus 1, which equals 3 meters. And this is for the first time intervals 0 to 3 seconds. Okay? If I want to know how fast it was going during that time, I want to know its velocity. That is change in position over time. That equals 3 meters in 3 seconds, because it took 3 seconds to get there, which is 1 meter per second. Now what's interesting about this is this change in position is really from here to here, or if I drew that over here, from here to here. Okay? And the change in time, this t, is really this time from here to here, which means we have rise over run, which means we've really got slope. So what I can say is velocity equals slope of a position time graph. Okay. Well, what's cool about that? Well, remember, this is a line, and if we know the slope, we almost know the whole equation of the line. Remember, a line has the equation y equals mx plus b, where y is the y variable over here, x is the x-axis variable down here, b is the y-intercept. Okay? Well, the y-intercept is where the line crosses the y-axis. For us, the b is the initial position. That's where it started, because that's where it is at time 0. It started at 1 meter. And m is, of course, the velocity. It's how fast and what direction it's moving. So I'm going to actually be able to write an equation for this line that would allow me to calculate where this thing would be if it had continued with that velocity. So what I can say is its final position, xf, is given by the velocity, the slope, times t, the x-axis variable, plus wherever it started, xi. So this is a linear equation, but we replace the y equals mx plus b with what they actually mean. Final position is equal to velocity times time plus initial position. So we have this awesome equation, and we can use it in a couple different ways. So if we know that one equation, we know how to find where something's going to be. We also know how to find something's speed, or at least its velocity. And so if we take this equation, final position equals initial, or velocity times time plus initial position, and we solve it for v, what we get by subtracting xi from both sides is xf minus xi equals vt, and then we divide both sides by t to get velocity equals xf minus xi over t, which is velocity. So this one equation for velocity is also the same equation for calculating final position. You just have to do a little bit of algebra to either solve it for final position or solve it for velocity. You could do a little bit more algebra and solve it for initial position if you wanted to. So if we had a problem where I wanted you to graph something or predict where something was going to be, let's say that. Let's say I give you this problem. I say, here's an object, and let's see, 1, 2, 3, 4, 5, 6, and I'm going to go ahead and I'm going to scale this in minutes. So 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes, 12 minutes, time in minutes. And over here I'm going to have position, and we'll give this position in meters, so x in meters, and we'll go with 5, 10, 15, 20, 25, 30, 35. And I'm going to give you a line that looks, oh, I don't know, starts at 5 meters and in 10 minutes goes up to 15 meters. I want to know, where's this thing going to be at 30 minutes? Where will it be at 30 minutes? Okay? What I'm really asking then is what its final position is going to be. So I want xf, question mark. Well, let's look at our graph and see if we can figure that out. We can figure out its speed by taking the rise over run, finding the slope. So the velocity is equal to, well, it goes from 5 to 15, so that's 10 meters, and that took 10 minutes. So this is 1 meter per minute. There's the velocity. And our initial position is 5 meters, so we know that xi equals 5 meters. We just pull it right off of the graph. And so I know xf equals velocity times time plus my initial position. Okay, so now I can just put in my velocity, 1. I can put in my time. I'm interested in this at 30 minutes, 30, plus my initial position, 5. And I get my final position. Well, 1 times 30 is 30. 30 plus 5 is 5. So xf equals 35 meters. Okay? I know exactly where it's going to be because I could find the equation of the line. And so it allowed me to solve for that.